What's up, guys? This is Mr. O'Brien again. This is going to be part three of atomic number and isotopes, and in this small mini lecture series, we're going to talk about how to calculate atomic mass. So I want to quickly give you an analogy of calculating atomic mass. So imagine I give you a baggie with a new element, and that element I call it candium. And in this baggie of candium, right, you have these types of isotopes. And as you can tell, we have different types of candies, right? We got some of these guys are candy corns, some starburst, and some pumpkins. And I can't really call them pumpkins or starburst or candy corns because they're all candies, right? And so what makes them all candies is that they're all taste sweet. They make life good. They contain sugar. But what makes them different in this case in chemistry is it's the mass, right? So in this case, each of these candiums has a mass of 2. And each of these candiums has a mass of 5, and each of these pumpkins has a mass of 7. So the pumpkins are clearly heavier than individually as any of these ones are. But would I calculate a atomic mass of, say, a periodic square of candium, which is the question that I want to get to? How do I do that? Well, first we need to address the natural abundance. As we can see here, there seems to be way more candium-2s present than any other types of isotopes. When we address that as a natural abundance or as a relative abundance, we can create percentages out of them. If we add them all up, if you can add them up on the screen, you'll find that there's a total of 21 candies, 21 atoms. But the abundance of each of these essentially is a fraction. So the candy corns, we're going to have 16 over 21. The starburst, we're gonna have 3 over 21, and then the candy, and then the pumpkins, we're gonna have 2 over 21. So when we multiply them by 100, you'll get these percentages, right? But what we're really focused on is this fraction base, right? That relative abundance. So now, how does the relative abundance affect the atomic mass? Well, if you recall in our previous discussion about atomic masses, it really reflects the isotopes that are most abundant. And so here we should expect that our atomic mass is going to be near the candium-2s because there's so much more of them than anywhere else, right? So let's go ahead and take a look at how we can do this. As you can see, my prediction is correct, right? The average atomic mass, 2.989, is really close to the candy corn's mass. So how did I get that 2.89? So what we want to do is we want to multiply the mass by this relative abundance. And how do we get this number here? Well, this number is essentially the fraction number above here, right? So that number is this. Essentially, when you get 2 over 21, you're going to get that decimal number. This number here is here, right? The starburst. That is 3 over, I should write it down here, 3 over 21. That gives you that decimal number. And then 16 over 21 will get you that decimal number, right? 16 over 21. And what we do then is we multiply the masses by those relative abundance. We'll get a series of subtotals. We add these subtotals up to get the weighted average. And as you can see here, the weighted average is clearly relying more on the candy corns than anywhere else, right? So let's move on with that idea, right, into having some sort of presence in chemistry, right? So a recap, what we need to do to calculate atomic mass, we first need to know the number of isotopes that we are naturally occurring, right? And then once we know the number, we need to know each isotope's mass. And then once we know each isotope's mass, we need to know their relative abundance or natural abundance. So take a look at the example provided of potassium, right? So potassium is the same example we've been given in the other lectures. The abundance of potassium 39 is 93.3%. In a fraction, this would be 93.3 over 100. In potassium 40, the relative abundance is 0.012%. So we can also identify this as a relative abundance by dividing it over 100, right? And then we can do this one as well. The percentage of potassium 41 in the world is 6.7%. So that essentially becomes 6.7 over 100, right? These are how you get these numbers. And so now that we have those numbers, we need to multiply those by the masses. So you'll see the mass here will multiply that mass times this relative abundance. Multiply that mass times that relative abundance, right? Multiply this mass times that relative abundance. And when we multiply them, we're going to get a series of sub numbers. Now, before I multiply them, I want to make sure that you can predict. And I'm going to look at the periodic table. And when I see the periodic table, I should note that this is the average atomic mass, as we already talked about in the previous lectures. This clearly shows a weighted average, closely showing more potassium-39's effect than the potassium-41 or 40. So our essential mass here, our atomic mass, should look something similar to that. So let's see what we got, right? We'll get 36.387 plus 0.0048 plus 2.47. When we add those all up, we'll get 39.138. And that's approximately the mass, the atomic mass of the one that you see on the screen on the periodic table. If you round it, it's 39.1. Now, why is it not the exact same? Well, there's a couple of problems, right? You know, maybe we're rounding, right? So there's some rounding errors present, right? It could be that we're not actually calculating, not using the actual correct mass because maybe we're not incorporating the electrons in these cases. As you notice, these are whole numbers, which is totally fine because, again, electrons are really insignificant in terms of the mass, right? But those are some rationales as to why these guys don't match up, right? But that's how you do it. That's how you get the atomic mass of the element given the known isotopes, right? Given the masses of the known isotopes, and given the natural abundance of each isotope, right? So here's another problem that I want you to try out. Take a look. This is the one for chromium, right? And as you can see here, chromium's got 4 isotopes. But try to predict before you answer the question of calculating the atomic mass. What should the atomic mass closely resemble? And when you calculate your answer, and if it resembles that, then you're on the right track. If you have any questions on this problem, hit me up at tutorial.